Hi, everybody. So we have been talking about reactions of acid bases and what we get as products for reactions of acids and bases, and being able to do calculations and things having to do with that. Now we're going to start talking about the process of titration and specifically acid-base titration. So we need some terminology. The first is a titrant is the solution that we know the concentration of that is placed in the burette. That's the long, thin tube. Um, then that is usually added step by step in a systematic manner into an unknown solution that is usually in the flask or the container underneath the burette. Okay. Something important for us to know and be able to remember over and over again. So I'm going to underline it. The equivalence point is a terminology that means this is when the acid moles equals the moles of the base. And that's going to be really important to us because we can remember that molarity of the acid times volume in liters of the acid is moles, and that's going to be equal to then the moles of the base, or the molarity of the base times the liters of the base. And so right away we can see that, oh, if we know that these two things, oops, I wrote acid and not base. Let's see if I can get rid of that part there. Okay. Liters of, if those are equal, molarity times liters equals molarity times liters, then if we're missing one of them, say the molarity of the acid, we can actually use that information. Let me erase this a little bit and rewrite it. We can actually use that information, the other information, to solve for what is missing. Okay, so to this point, you should have some things written in your notes. And the first one is, what is a titrant? And it is its function is to be added to a solution of unknown concentration so that we can reach something called the equivalence point, where the moles of the acid equals the moles of the base. And at that point, we can do some calculation to try to figure out, okay, what is the molarity of the acid that is missing, or the base, what have you. All right, another terminology that we need is called the endpoint of the titration. And that titration endpoint is when the indicator changes color. It might be where we have the actual equivalence point happening at the same time as the indicator changing color. That is really what we want. We don't want the indicator to change color and tell us to stop titrating if we have not reached the equivalence point. So that's when we want the two to be the same. All right, and this is all known as volumetric analysis. The terminology here for what is happening, and I'm going to erase my writing, for what is happening is called a pH or titration curve. And so that's what you see here. In a pH or titration curve, as you see in the picture, we have pH on the y-axis, and we have volume, pH on the y-axis, and volume of the NaOH, or what have you, on the x-axis. And the volume on the x-axis usually is the thing that is in the burette. It's also the thing that we already know the concentration of. Okay. As we've learned already, that the net ionic reaction is going to be hydrogen ions plus hydroxide ions yields water. We are going to be able to keep in mind that when we have a strong acid with a strong base, what we really have is no equilibrium happening. Instead, what we have is easy pH to calculate. The important thing to remember is that pH, and you'll remember this because we've been working with this for a while, pH is equal to, if we have a strong acid, strong base, and that's for this situation only, we can figure out that the pH is easy to calculate because we can determine the negative log of the hydrogen ion concentration. All right? So we're specifically still going to be talking about that pH calculation. Big important thing right here. Big important thing. In a strong acid, strong base reaction, At the equivalence point, our solution is neutral and our pH equals 7. We do not have equilibrium. We will be doing some stoichiometry. We do not have any equilibrium here, but we can also determine the number of moles of H left after the reaction, and we can figure this out, figuring out what the pH is. Sorry, need a Kleenex. Okay. Now, what about, I'm going to go erase that, go back to here. What about if we don't have a strong acid and strong base? What about instead if we have a weak acid with a strong base? And you are going to be wanting to pay attention to this week, weak acid with strong base, because this is going to be the type of titration you are going to be doing in your laboratory exercise today or this week. We're going to break these down into 2 steps. The first step is going to be that we are going to complete a stoichiometry problem. And second step we're going to complete is an equilibrium problem to figure out the position of the weak acid, and we must determine what the pH is. Things to know. If we have a strong base with a reaction, it is assumed to go to completion. That means that the pH before the equivalence point can be determined. Halfway to the equivalence point, another important spot, our acid concentration is equal to the anion concentration. So then we have Ka would be equal, and we're going to talk about all these in far more detail. So at the halfway point, pH is equal to something called the power of the Ka, or the pKa. All right. Right now, I know that doesn't mean very much to you, but we will come back to that. Okay. Here's the big important thing. At the equivalence point in this type of reaction, remember this is a weak acid and strong base. At the equivalence point, the pH is greater than 7. At the equivalence point, the pH is greater than 7 because what's actually made, because you're working with a strong base, it is going to be making a basic salt, which causes our pH to be higher than 7. As you can see in this picture, at this equivalence point, pH is going to be higher than 7, so it'll be a 9 at this equivalence point. Okay, how do I figure out pH at the equivalence point? Usually it is halfway up the vertical rise. So if my vertical rise is a total of 9 pH points, halfway is telling me that I'm going to have 4.5, an increase of 4.5. And if my vertical rise started at 3, 4, 5, 6, at 4, 4 plus 4.5 is giving me somewhere around 8.5. And as you can see, that is at best, that is an estimated value. That might be 4.5 where we started there. So we have to be able to pay attention to that. But the 3 to 12 is from the beginning to the end. What is the rise? And if we started at 4.5, then the vertical rise, half of the vertical rise is going to give us the increase in the amount of pH. And in this case, that gave us a 9. Okay, let me erase because I've scrabbled the heck out of that. And let's continue on. Okay, something to think about, and I wanted to bring both of these up at the same time. So with this picture, the pH, another thing to know, facts to know, the pH at the equivalence point is determined by the Ka. So if we can figure out what the Ka is, the smaller Ka value, the higher the pH. In other words, the weaker our acid is. The smaller the Ka value, the weaker our acid is. And so that's an important thing to be able to remember. And that, please also remember, Ka and Kb are opposites of each other. And for your own enlightenment, Ka times Kb is going to come out equal numerically to exactly 1 times 10 to the negative 14. That should look familiar because that should bring to mind the entire pH scale, and you're absolutely right. That's exactly what it does. So Ka times Kb is the same as 1 times 10 to the negative 14. All right, we're going to continue scrolling here. All right, we can turn this around and start with weak bases being the thing that we need to know the pH and thus the concentration of. So we would have the strong acid be added to the weak bases. It just changes the direction of the um, of the pH titration curve. Okay, so what we're going to do now, and what you're going to want to do, is follow along as we work through some problems. And so our first set of problems is going to be if we have a reaction between hydrochloric acid and sodium hydroxide. That means that we have a strong acid and strong base. So this is our situation of a strong acid with a strong base. And so we're looking at it, and it's asking us what is the pH at each of the following points in the titration of 25 milliliters of 0.100 molar HCl being titrated by a 0.100 molar NaOH. Okay, so the thing that we want to know each time is what is the pH of that solution. And so first thing we have is before the addition of any NaOH. So what we actually have before the addition of any NaOH is we have 25 milliliters of 0.100 molar HCl. And HCl is our strong acid, so no need for a rice table when we have a strong acid. Instead, we just get to go straight to the calculation of pH. So pH is going to be the negative log of 0.100 molar. So 0.100. And if you've been paying attention, you know already that if this is, that's 10 to the negative 1, and that is what we have, then the pH is going to be 1. But let's make sure we use our number of significant figures correctly. We will make sure that our pH is written with 3 significant figures, 3 decimal places, because we have 3 significant figures. Okay, so far so good. Let's go ahead and move on to the second situation because we have not added any NaOH here. And so we're going to go ahead and add in the next part. So I am actually going to erase this so I can keep scrolling up.